In our previous video, we estimated how the df dx, the change in z per unit change in x, how that slope itself changes when we increase y by a little. So we estimated df dx at the point 1, 2, and then we estimated df dx at the point 1, 2.2. This is very much in line with what we're observing up here. We asked what happens to the slope of the surface, the three-dimensional surface, at the particular cross-section if we were to move over to the next cross-section. And now we want to just show that that answer that we get is going to be the same if we had first calculated df dy and then looked at how that df dy changes if we increase x by a little bit. So we can interpret this as follows. If we are at the point xy equals 1, 2, we estimate df dx is equal to 16 units of change in z per a 1 unit change in x. That's our answer here. If we increase y by a little bit, df dx becomes 22.3 units of change in z per a 1 unit change in x. So the surface is a little bit steeper if you increase y by a little bit but retain the same x value. Thus the change in z per change in x increases by 6.3. But that note is only for a change in y of 0.2 units. So we kind of estimate that if we were to unitize this, right, because we always want to think about rates as how much per 1 unit. So if it represents a 6.3 unit change in y per a 0.2 unit increase in, in z per a 2.2 unit increase in y, then we would anticipate that if we were to increase y by 1 full unit, the slope of z in the per unit change in x would increase by 31.5. We should get exactly the same answer if we look at the change in z per change in y. So here we are again at the point 1, 2. The df dy at that point would say, well, what happens to the z value if you increase y? Well, if we increase y, we notice that the f sub y at the point 1, 2, the z value changes from 8 to 10.65. So that's a 2.65 unit change in z for a 0.2 unit change in y. And that comes out to be 2.65 divided by 0.2 is 13.25. Now, if we increase x by a little bit, so that means we're now over here, where the least we can increase x is by 0.1 unit, and if we look at that slope, the slope in the y direction at the point 1.1 comma 2, so we've changed x a little bit, but we've kept y the same. The slope in the y direction, y will go from 9.6 to 12.88, and that change is 3.2 units of z, divided by, again, a 0.2 unit change in y, which comes out to a 16.4 unit change in z per 1 unit change in y. So we notice that when we changed x by a little bit, our f sub y, by changing x by a little bit, went from 13.25 to 16.4. That's the change in our slope. So our slope changed by whatever the difference between these two units is. And how much did we change x by? Well, we changed x by 0.1 units. And that difference comes out to be, let's see, 31.5. Not surprisingly, we get 31.5 once again. And that just goes again to verify that we get the same partial derivative. If you think about it, we're kind of operating in a rectangle, whether we look at the changes here vertically and then compare those vertical changes, or back here in the table, we look at the horizontal changes first and then compare them vertically, we're going to end up with the same number. And the interpretation would be much the same. That is, if we're at the point xy equals 1, 2, we estimate df dy to be 13.25 units change in z per a 1 unit change in y. If we increase x by a little bit, df dy becomes 16.4, thus the change in z per change in y increases by, what is this difference? 3.15, which would come out to a 31.5 unit change in df dy per a 1 unit change in x. So that's what I mean by similar interpretation. Let's put this into a context of a problem. It isn't super often that we're interested in interpreting these values. We're going to use them to help us calculate things like maxima and minima and saddle points on three-dimensional surfaces. But let's think about a practical interpretation of the second-order partial derivatives. So this is an example that looks at a string, like a guitar string, and the string is 1 meter long, and at time t seconds, the point x meters from one end is displaced f sub x of t meters from its rest position. So here we have a 1 meter long string, right? A string that's 1 meter long. And that string is going to be, think about it like a guitar string. Whenever you pluck it, the string vibrates, right? And so at first, when you pluck that string, 1 second later, it may look like this. And so the value of f is the height of the string. And so maybe 1 second after that, the string is up a little bit higher, and then maybe after that it starts to return and recede down and starts to vibrate the other way and then the other direction. So these are all the different kind of positions of the string, which you would see if you looked at that string vibrating. You would kind of see it oscillating back and forth, and these different curves could be at different times. So this first curve that we drew could be t equals 1, and maybe this guy is t equals 2, and maybe this is t equals 3 and t equals 4, and then it maybe bounces back down at 5, 6, 7, 8, 9, 10, 11, 12, and so on and so forth. So we want to look at the 4 second-order partial derivatives and to interpret them at the point 0.3, 1 and describe the meaning of their signs in practical terms. So first of all, for this function, we compute the 2 partial derivatives, f sub x and f sub t. And you can see that with respect to x, you're going to get a cosine, and the value of pi comes out using the chain rule. Similar thing for t, we take the derivative of sine of 2,765 t, which is cosine of 2,765 t times the derivative of the inside, which is that. And again, using Wolfram Alpha, we can compute these. So here we have the second partial derivative. And once we have this computed, now we're going to plug in 0.3 for x, 1 for t, and the value that will come out of this is negative 0.01. Now remember here, t is measuring time, not degrees, like an angle measure, so we should be in radians. When we compute the derivative of the first derivative with respect to t, we get this function here, which notice is identical. Sorry, not identical. This is not the mixed partial. It comes out to this expression. And now if we plug in 0.3 for x and 1 for t into this equation, we get negative 7,200. So to begin thinking about these values, we should probably get some units first. So we know that f is the height of the string. And that unit of measurement, what do they tell us? They say the point x meters from one end is displaced f of x comma t meters. Okay, so this is in meters. This is the height of the string in meters. X is the position from end of string. Again, this is going to be measured in meters. So remember, we have that string suspended from one end, and then where we look at the string, whether we look at the string here or here or here, is going to correspond to different heights, right? So like even at t equals 1, depending on what value, where along that length you are, when you're here, the height is a little bit perhaps smaller than when you move closer towards the center of that string. Like right here, that height is going to be a little bit higher. Same thing for here and here. At time 4, the height of the string closer to the end point is going to be a lot less, right? Because that point can't really is more stationary than in the center, where you're going to experience more of a vibration. So that being said, we also need to define t, which is going to be measured in seconds. So now we can easily get our units. So f sub xx, remember, is the derivative of f with respect to x, and the derivative of that thing with respect to x. So if I look at the units, f has units of meters, x has units of meters, and then if I take the derivative of that with respect to meters, that's going to be meters over meters per meter, which is going to be meters per meter squared. Okay, but this is height, right? So meters of height, what we're basically asking for, what's happening to the slope of the string as you go along every meter. So let's draw a picture of this. So here's an illustration of our string, and we're saying that if we change x by a little bit, right? So x means if we look at a slightly different position on the string, right there, and we change that value of x by a little bit, we're asking for what happens to the slope of that string. And we see that the slope here is is greater than the slope over here. The slope at B is less than the slope at A. This is our physical string right here. It's suspended on both ends. And we're saying if we change x by a little bit, maybe that's to 0.4, we're asking for what happens to the slope of the string. And another thing we could say is that the string is concave down. The string is concave down. How do we know that? Well, because the second order partial derivative is a negative 0.01, which tells us that the function is concave down. When we look at the second partial with respect to t, the units that we're going to get, so let's write this another way. We'll write this as df dt, so that is meters per second. And then we're going to change the value of time by a little bit, so we'll have meters per second, right? So if we take meters per second and multiply it by 1 over seconds, we'll get meters per second, which is meters per second squared. And one thing we know about meters per second squared is it is the acceleration of the string. Okay, so let's look at a picture of that. So here we are at x is 0.3, and we want to know what happens to the how fast the string is oscillating when we look at it one time unit later. So at this moment in time, I had the wrong picture up here. So again, when x is 0.3 at our position, we want to ask what happens to the speed of the string. So you can think about meters per second as the speed of the string 1 second later. So if here we are at t equals 1, so we are at x equals 0.3, t equals 1. If we look at how fast the string is moving there, it is moving more rapidly than a little bit of time later. So here the string, you can notice that that little vector is shorter than this vector here. And that is telling us, and we know that rather, because the concavity of the function is negative. So that means the function is concave down, and we could say that the velocity at b, a time unit later, is less than the velocity at a, 1 time unit before that. So it's basically telling us that the string is slowing down. Its velocity is getting shorter. Now the mixed partial, first of all, we notice that they're both the same. They both come out to the same value, and if I plug in x is 0.3 and t is 1, I get positive 14. Let's look at the units of that. So here I get the change in meters per second per meter. And I could write this as meters per second, that's how fast the string is oscillating, if I move over horizontally a little bit. So here the string is moving faster